MAE 3123, Manufacturing Processes, lecture number 3. I know that we had covered up to um, maybe like 10-15 slides in this lecture, but just for the sake of continuity, I'm going to cover this entirely in this lecture, okay? And then I will also post the video for, the lecture for chapter number 4, okay? So, um, in this lecture, we are going to be talking about um, the structure and manufacturing properties of uh, mainly metals. Um, and so, why do we want to talk about that? As I explained to you in the class, the reason is because the structure and properties of these materials is going to define the manufacturing process. So, if you know the properties, then you can define your manufacturing process. As I asked you, the question was, what do you decide first? Do you want to decide the properties first and then the manufacturing process, or the other way around? Typically, most of the time, we decide the required properties for your design applications and then decide what material we will choose and then decide the manufacturing process. So here is an example of a turbine blade for jet engines. As I mentioned to you, one of the reasons why I want you all to look up the new additive manufacturing processes that are being evaluated for um, a component such as the turbine blade is because the way these blades are made right now, it can take a long time. It can take a couple of months to finally get the final properties. And that's because how your how long your turbine blade is going to last is going to be based on the manufacturing process. Um, so there are three different methods that they have chosen in the past. One is they do conventional casting. Then they do directional solidification. So they just cast it starting from the bottom and then they start casting to the top. Um, and that gives you what are called columnar grains, and that has better creep resistance compared to these conventionally cast blade components. And then the third one, which is the more uh, expensive variety, but that is also because they are much longer lasting, and that's because you get a single crystal. And as I mentioned to you, the lesser the number of grains, the better the creep properties are. So if you have only one single grain or a couple of grains only, then those components, those blades are going to last you a long time. And the reason is that many times creep is a hidden killer, and this component can fail in service, which means that once it breaks, it is rotating at a very high RPM and it can go and bang up against the wall of the blade, wall of the engine, and make a hole, which means that the engine can fail right in service. You do not want that. And that is also the reason why you change the components after a certain number of hours. If you have designed it for, say, 10,000 hours or whatever, you change those parts anyway after 10,000 hours. Okay, so and these blades are made by a number of different manufacturers. For example, these are for the Pratt and Whitney engines. You have similar processes for the GE engines and so on. And now GE is more focused on making those blades by 3D printing. I recommend to you again, please go and check the 3D printing process for turbine blades on the GE um, I think it is called GE Tech reports. Please go and look that up. Okay. So why are we bringing this discussion about the crystal structure of these materials? I think I showed you um, the what is called the SN curve. S is the fatigue stress, the stress during the fatigue process, and N is the number of cycles. So if you plot that for different materials, if you take a body-centered cubic material that has much lesser fatigue life, in fact, you might even find what is called a hockey stick type of a um, uh, pattern. And that hockey stick, the bottom of that hockey stick will tell you the maximum stress that this component should be experiencing in service. And that is because these materials will tend to creep much faster than a face-centered cubic type of a material. Why? Because body-centered cubic is only 68% dense, whereas a face-centered cubic material has 74% densification uh, of that crystal cell. So, which means that the atoms uh, can move around much more easily in a body-centered cubic type of a structure than a face-centered cubic type of a structure. So, which means that these materials can creep much faster than a face-centered cubic type of a material. So common BCC metals include chromium, titanium, and tungsten. The face-centered cubics are the cells are at the center of the faces as well as at the edges, and these are the common materials are aluminum, copper, gold, and silver, or even nickel for that matter, and they are much better in creep type of applications, but they are also good for fatigue, and they are also good for deforming into different shapes and forms that you want for different applications. But then why don't we choose a face-centered cubic type of material for all applications? Why do you choose, say, body-centered cubic still or hexagonal close-packed still? And that's because there are certain applications for um, certain materials, and only those materials are going to work in that kind of a situation. So how do um, a, a crystalline type of a material deform permanently under a tensile load? So when you did tensile testing in ENSA 3313, you just saw this sample just extend and elongate. You didn't really look at the side of that um, tensile test sample and observe that they had these kind of striations. And why does this happen? It's because, I mean, as I said to you, it is similar to moving a carpet. So if you have a heavy carpet, how do you move that? You have to create a wrinkle and you move that wrinkle. So if you have a block of atoms, you apply a shear type of a stress on one side, so you create a wrinkle on one portion of that crystal, and then you start moving it slowly, little by little. Okay, so when that happens, that sample will start moving these atoms along the plane that has the maximum number of atoms. Okay, and you do not know where those atom planes are going to be. So they can be at an angle to this to this tensile loading axis. So they will tend to move, those atoms will tend to move along certain preferred directions and orientations. Okay, so there are two ways in which these crystalline materials can deform. One is by a process called slip, and the other one is a process called twin. So slip is the process by which the, the material moves like a carpet, and twin is you have a central location or central plane and you just bend it around that plane. Okay, and then you just shear that in such a way that it moves. So obviously you can see that these atom planes can move much more easily during the slip process than in the twin process. Okay, so but certain materials will prefer to deform in this manner, whereas certain materials will prefer to deform along this manner. FCC and BCC type of materials will tend to prefer to deform in this type of a deformation process, whereas HCP will try to deform along this type of a process. Okay, as I said to you, the movement of atoms can happen much more easily if you push the atoms in such a way that you are creating a wrinkle in that plane, and the movement of those atoms happens along more easily along this plane of atoms, which is the maximum number of atoms, is called the slipping plane, and each material has certain number of planes that this can happen most easily on. So you have a direction of the movement of the atoms and the plane of atoms on which it can happen. So the combination of the slip plane and the slip direction is called the slip system. Okay, so most of the materials can deform in a way that they will happen more easily along a system of a slipping plane and a slipping direction. Once these atoms will start moving, they will, suppose you are moving a set of atoms along the slipping plane. If it goes and hits up against a wall, it will stop. So similarly, the movement of atoms will stop after it has moved a certain distance. So then it will go to the next more suitable slip plane, slip direction combination. And then once that ends, you go to the third one and fourth one and so on. So for face-centered cubic type of materials, there are 12 such systems. There are 4 atomic planes where slipping is preferred, and there are 3 directions where slipping is preferred. So the total would be 4 times 3, which is 12. Okay, so similarly in body-centered cubic also you have 12 such systems, 4 slip planes and 3 directions. But why do you think slip is more easy in the face-centered cubic type of materials compared to body-centered cubic type of materials? It is because of the type of stresses that are required in order to make those atoms move. So in face-centered cubic, it is much more you need to apply much lower type of stresses. So aluminum, it is much easier to move those atoms and atom planes. Whereas in the case of body-centered cubic iron at room temperature, those atoms are bigger and they're heavier and they require much more stresses to move them. So you require much higher tensile loads to make a steel sample fail compared to an aluminum sample fail. So does it make sense? So please do ask me questions if you have any questions about this. Okay. So typically slip happens because of the shear stresses that are applied on this material. So why do I call this shear? Let me show you this. So we saw here that even though we are applying this load in the tensile direction, the movement of these planes happens at an angle. So if you have these planes at an angle, you are actually shearing those planes one on top of the other. Okay, that's why we call this a shear load for making a tensile failure. So you are creating this stepwise failure or movement of these atoms, and once they start moving, after a while the cross section of your sample becomes thin enough that it is no longer going to be able to take the load. So then the sample will fail. So that is only for a tensile test. But when you are manufacturing a component, do you want to make the material fail? Absolutely not. So then what do? You only want to apply enough stress in such a way that the atom planes will start moving, but they will not detach from each other. So you only want to apply enough stress to make the material move or deform, but not to fail. So you have a clear-cut distinction between a tensile test and a deformation process. So here in the deformation process, you're only going to make the atom planes move enough, and you apply the enough load such that it will not fail, but it will also not go back to the shape it was originally before you started the deformation process. So you have to apply in manufacturing process, you have to apply enough plastic deformation. You have to create the plastic deformation. And if you recall the tensile stress strain curve, you have you go past the area where the stress strain curve starts curving over, but you don't go enough that it goes over the hump. Then in which case it will start failing. You do not want the material to fail, but you want the material to deform plastically. And when do you stop the deformation? You stop the deformation such that you make enough deformation such that those grains will start deforming, and then they will go and stop. They will get stopped by the next surrounding grain. So it can only move a certain distance. So it can only move a total of say 5, 10, 15, 20% strain. If you go beyond that, it is going to make the component fail. You do not want to make the component fail in a manufacturing process. I hope you are understanding what I'm trying to say here. So, just to reiterate, slip will happen more easily in the planes where there are maximum number of atoms. Why do I say that? The reason is those planes where there are maximum number of atoms are also have the maximum distance between one plane and the next. If you are shearing two sets of, suppose you take a stack of paper. How do you make one set of sheets of paper slide over another set of sheets of paper? You have to shear the one set over the other, and the distance between those planes is the maximum where the plane of atoms have the maximum number of atoms, because it requires the least amount of force to move that one set over the other. Okay, so that force is also called cohesive stress, and it is based on the distance between the row of atoms. So if you have a plane of atoms where there are the maximum number of atoms, as I said to you, they are the farthest apart between one plane and the other in the crystalline material. So it is easier for you to move that one set over the other. Okay, so that is also dependent on the total amount of stress that you are going to apply, and it requires the least amount of stress to be applied in order for you to be able to move those atoms apart, move those atomic planes apart. The other kind of movement of atoms happens due to creating defects. I think I also mentioned to you that one of the reasons why we can make materials deform is through the formation of defects. You know that, as I said to you, you should know that all materials have defects, and those defects can happen or can help us to deform the material. For example, if you have if you have a, a vacancy of an atom, that now you can move this atom here, which means that now you are creating the vacancy here, and so this can move into that location. So these atoms can start moving from one position to another because of the presence of defects. So suppose instead of one vacancy, you have, say, 100,000 vacancies. So which means that 100,000 atoms are now free to move from one location to another. And so if all those 100,000 atoms just combine together, you are going to be creating a huge gap in that material. So now you can create a deformation or create a dip in this material. So when you start out, all those vacancies are not together. Okay, so they will start moving one over the other, and they will all start um, moving together, and so all those vacancies can come together and then um, move from one location to another. See, the other way would be you have another type of atom that is inside the gap of this crystalline lattice. So you are creating internal stresses between those atoms, and then they will start um, being able to move from one location to another. And sometimes this substitutional, it is called a substitutional atom, and that atom might be smaller than the other atoms in the lattice. So which means that you are creating a gap, and that gap can move around. So the whole material can deform as a result of those substitutional atoms. So see that, or you can also create what is called a self-interstitial atom, but that is much rarer than the vacancies and the substitutional impurity atoms, okay, or interstitial impurity atoms. So these are the defects that can help us to deform blocks of atoms or blocks of material. The other way to do it would be to move sets of planes of atoms, and those sets or planes of atoms move. That defect is called a dislocation. So this vacancy is a single atom, whereas a dislocation is a line defect. And there are multiple types of defects. For describing them in a simplistic manner, there are two types of dislocations. One is an edge dislocation, where you have these atoms, sets of atoms, and then suddenly you are missing have one set of planes of atoms that are missing. Okay, so if you move this set of atoms over the other, then this defect can start moving from one position to another. So if you move this set of atoms, that extra plane of atoms will move from this side to this side. So it is similar to moving the carpet, ripple in the carpet. Do you understand? So after that extra line of atoms moves from this side to this side, you have moved that ripple in the carpet from this side to this side. Or you have another type of defect, a dislocation called a screw dislocation. So it is like you twist one set of atoms, one set of planes of atoms over another set of planes of atoms. But the reality is that no dislocation is completely an edge dislocation or completely a screw type of dislocation. So you have a combination of atoms. So you can have some shear dislocation, a screw dislocation, and an edge dislocation. So when you are deforming a block of atoms or a block of metal or block of an alloy, you are moving whole sets of atoms which can have some edge dislocation features and some shear location features. Okay, so that's how you are deforming a huge block of material. And now, I mean, this is only, but please remember that this is only a very generic way of describing the deformation of materials. How does it relate to your elastic stress or your plastic stress? How does this relate to that? Well, the reality is that you need to go beyond the elastic modulus in order to make those atoms moved by edge dislocations or screw dislocations. Okay, so if you look at the stress strain curve, if you can see where the elastic modulus is, so if you go beyond that, then you are actually creating the movement of edge dislocations and screw dislocations. So please understand this only in terms of describing the process, but the actual engineering numbers comes from your stress strain curves for any given material. Okay, so here this was what I was telling you. So you see this one. Okay, you have an extra set of atoms and you have created a ripple in this carpet. Okay, so you are pushing and pushing and pushing. So after a while it has that plane, extra plane of atoms has moved from this side to this side. And in order to make that happen, you have to apply a shear stress. If you define the stress required to deform a material, theoretically, they will always show much higher required stresses to deform the material than in real materials. And that is the reason is because most materials have defects which are like dislocations, and so it is much easier for you to deform this block of materials than you have a block where there is no dislocation at all, there are no defects at all. But the reality is that there are going to be defects in materials, which means that you will always find that the actual strength of metals is much lower than that predicted by the atomic theory. Now, when you are creating a casting, for example, or you are taking a material that is made by the solidification process. So how are castings made? Castings are made by pouring a molten block of material into a mold. Okay, so when that happens, I mean when you are doing it first, it starts creating nucleuses. So it starts solidifying at multiple locations in that pool of molten metal. And then slowly those set of atoms will solidify in specific locations in that pool of molten metal. And then once it is solidified, so for example, you take a glass of water and you put it into your freezer. So at first it is all completely liquid. If you go, I mean, if you are impatient, I mean, for example, you are creating ice cream. If you are impatient and if you go and open up the freezer again, you will see that there are certain locations where that water or the ice cream mix has solidified. But it is still, a lot of areas are still kind of gooey, right? As you freeze it much more, those groups of atoms have solidified and become big blocks. Over a period of time, this block is solidifying in one direction, this block is solidifying in another direction, the third block is solidifying another direction, and so on. So they all are solidifying in different orientations. So over a period of time, then this area where there is an imperfect solidification will start creating a line between this block of atoms and this block of atoms. And once this whole block is solidified, then this is a complete line. And this line is not a straight line. It can be squiggly type of line. So this is what you really saw when you polished a block of material and looked at it under the microscope. So if you had solidified that block of material, you will see that they have these groups of atoms in one location. So this is one grain, this is another grain, this is the third grain, and you will also see that this grain, the average size might be similar, but the size, the exact size of this block of atoms or the grain is different from the size of this block of atoms. So they are all at different angles where those grains will meet with each other. You should also note that the if you took this block of um, if you took this block of material and you applied a tensile load on it, you applied a normal stress in this direction, what will happen? They are all oriented in different directions, right? They will all have different stresses for making them move over the other. And that stress required to move those atoms or block of atoms is going to be based on the orientation of that grain with respect to the tensile stress. Now, in one small area of this material, there are probably going to be thousands and thousands of grains. Each of those grains is going to be oriented in different directions. So they are all going to be different. The stress required to move those blocks of atoms is going to be different. So how do you get an average number? So over this entire block of atoms and entire sets of grains of atoms, you have an average stress that is required in order to move those sets of atoms. So that's what you are testing by doing the tensile testing. So if you have an average size of grain that is pretty similar in a very narrow band of sizes, then the stress required in order to move these atoms is going to be dependent on the orientation. But it is going to be an average stress required for that. Okay, so it is also going to be dependent on the grain size. And if you look at the homework set that has been posted, there is one problem where we are going to be looking at the relationship between grain size and the average stress that is required. So if you had, say, 100 grains, do you think that if you increase the number of grains from 100 to say 10,000, which one will require a higher stress? So if you have 100 grains, those grains will all start sliding over each other and they will all start deforming. So they can only move to a certain distance. But suppose you increase that number of grains to say 10,000. those grains are all much smaller and finer. So when you start trying to deform that block of metal, those atoms, those grains will be able to move a certain distance and then get stopped by the next adjacent grain. So which means that increasing the number of grains makes it harder for you to deform your block of material. So the number of grains is going to be dependent on it is called the ASTM grain size number. And that ASTM grain size number is dependent on the number of grains found in an average area of 1 centimeter squared at a magnification of 100x. So there are equations to calculate all that. And so if you had ASTM grain size number 0, you had 8 grains per millimeter squared. So which means that there are 64 grains in 1 centimeter squared. So if you go to grain size number 3, there are 64 grains per millimeter squared. So which means that you have 64 times 2 in 1 centimeter squared. So you will be able to calculate that. So see that ASTM grain size number, if you increase it to 12, in 1 millimeter squared, there are 32,800 grains. So in 1 millimeter cubed, in one small volume, there are 4.2 million grains. Just imagine, I mean, there are so many grains. So so if you increase the grain size number to 12, it is much harder for you to move these sets of atoms compared to the grain size number 0 or grain size number 3. So this one will obviously have a much higher tensile strength compared to this material. So suppose you did cold rolling, which means that all the grains are oriented in one direction, but you have increased the number of grains tremendously. Okay, so if you have done cold rolling, that cold roll sheet will have much higher strength compared to an as prepared block of atoms. So if you want to increase the strength of your component while also making the component, you should roll them. You should be able to roll them. We will talk about all that when we go to the actual manufacturing process. So this gives you the understanding of what happens when you are creating a block of materials. Okay. One thing that happens is when you combine different materials, they can embrittle the other material. For example, if you add lead or bismuth to copper, they can embrittle copper. And that embrittlement means the block of materials are not going to be as strong. I mean, they are strong, but if you're trying to pull it apart or if you're trying to deform it, they can easily break catastrophically, and it can reduce the toughness of that block of materials. So suppose if you are adding 20% lead and 80% bismuth to copper, it can reduce the strength. So if you had So that's what happens when you are combining different types of materials. So if you are trying to alloy, you also have to look at what is the effect of adding one type of material to the other. Okay. So let's look at the deformation process itself for a block of materials such as in rolling or forging. Okay, so you take this upper block of materials. So idealized representation is, so all these are just in single locations and it is not deformed at all. Now, if you put it inside a set of a press, and start pressing it, and hopefully this is not going to bulge on the side and things like that. Okay, so what happens to these sets of atoms? They are kind of squished. Okay, they are kind of squished. And also assume that after you remove that press, that squishing remains in place. So which means that you have gone past the plastic deformation. So it will not spring back to its old uh, shape. And you will also see that these sets of atoms or sets of rows of atoms are all aligned in one direction. And suppose you took a set of rollers and you push this block through that, they will all tend to align in the direction of the rolling. And so it will get strengthened in the direction of the rolling, but it may not be strong in the thickness direction. So the properties have changed quite drastically in the direction of the pressing and um, the direction that is normal to that. So these are all going to be controlling your manufacturing process. So if you are rolling a sheet of material, so after rolling, as I said to you, it becomes anisotropic. And so when it becomes anisotropic, it can only deform to a certain extent. And if you try to go beyond that range of loading, it can crack. So for example, if you have an aluminum sheet, this is an example of an aluminum sheet. Um, you are pushing it through a set of rollers and it has created a crack. And that crack originally is not seen. So how do you know that? So if your manufacturing process is such that you're also rolling and you're also compressing, you're creating a kind of a divot or a bulge in that material. So when that happens, that crack can accentuate itself and can create the crack. So in this case, it would be a vertical dark line at the center. And it can only be seen while if you're doing a bulge test in that material. So again, we have mentioned all that in the homework set that was posted this week. So this is from chapter 3. So we talked about recovery, recrystallization, and grain growth. So this is a process that happens when you are deforming a material. So what is hot working or cold working? If you recall, I said that hot working, the temperature at which you work this material will be considered to be hot working if that temperature is above half the melting point in degrees absolute. So for example, if it is copper, the melting point of copper is, I think it is 1160 or something like that, 1160. So in degrees absolute would be plus 273. So which would be approximately 1360 plus 73, 1433. So half that would be 1433, 725 degrees degrees absolute. So in degrees centigrade, 750 minus 273 would be, so 750 minus 200, 550 minus 73 would be approximately 475 degrees centigrade. If you are above 475 degrees centigrade, you are actually hot working the copper material. If it is below that, you are actually cold working the material. So why I'm trying to correlate that to, say, a process like this. So suppose you did cold rolling, and you also try to deform it in the third direction. It can easily create the crack in in that material. But suppose you want to avoid that, what would you do? You would do hot working, and then you are creating small grains, and then if you heat it up slightly, what happens to those small grains? They will all start combining and becoming a large grain, and then they will all start recrystallizing into smaller grains or slightly larger grains. And then if you keep continuing to heat up that block of material, you are going to be creating larger and larger grains. So this one schematically shows all the process as you are doing the heating the block of material after doing the cold rolling. So originally when you did the cold rolling, all the grain sizes have become completely small, and it shows much higher strength, and the residual stresses are also much higher. But suppose you start heating it up, what happens to the grain size? They will all start combining into larger and larger grains up to a certain extent. But beyond, I mean, if you increase the temperature beyond a certain um, limit, then those grains will all start combining together and becoming larger and larger grains. So you recover the ductility of that material. So suppose you start with a 1 inch of steel, you cold roll it. Okay, the strength goes up, the grain size goes down, the residual stress also goes up. And then you do heat it up above the hot working temperature. After a short time, then those strength actually starts going down drastically, and then the grains will start growing, and you recover your ductility completely. So what does it tell you? If you combine this recovery, recrystallization, and grain growth process with your cold working, then you can actually deform your material as much as you want. I mean, not 100%, but it is much easier. So that's the process by which we make really large components, really thin shapes. So if you make a thin shape, you do not leave it in that shape. Okay, you heat it up such that you recover some of that ductility back. You remove some of the residual stresses. Why? Because if you have residual stresses, those residual stresses can actually work against you in the actual service itself. So you recover some of that ductility, because increasing ductility actually increases the toughness of your material. And The other thing is that if you have done cold working, it makes it an anisotropic material. You do not want that to be the case if you can help it. Okay. So, and how does this correlate to the um, increasing temperature, increasing heat treatment temperature, or increasing reduction and things like that? So, if you take a block of material and you applied a certain amount of cold working, and then you took that same block of material and you put it into a hot furnace. This one is at a lower temperature compared to this block of material. So if you applied heat, say 100 degrees centigrade, the strength does go down, but if you had taken up the temperature to 125 degrees centigrade, the strength would have gone down much more. So why is this important? So suppose you have a block of material and you want to, and you started out with 1 inch and you actually want to go down to 0.1 inch. Can you go down from 1 inch to 0.1 inch in one step? Not possible. So you have to take it to say 3/4 of an inch, heat it up such that the strength actually goes down, and if you can help that, you can actually increase the temperature to say 600 degrees centigrade compared to 400 degrees centigrade. If you went down to 400 degrees centigrade, I mean, if you heated it to 400 degrees centigrade, you may not increase the, I mean, you may not decrease the strength to the same extent as if you went up to 600 degrees centigrade. But suppose instead of increasing the temperature, if you took 1 inch of that block and if you went up to say 0.9 inches and you heated it up to 600 degrees centigrade, the strength does go down, but the strength has not, I mean, after cold rolling, the strength has not gone up that much. But suppose instead of 0.9 inch, you went up to say 0.8 inches, the strength actually goes up, and when you heat it up to 600 degrees centigrade, it actually loses the strength much more than in the first case. But suppose instead of 0.8 inches, you went down to 0.7 inches. And if you heated it up to the same temperature, the strength after cold rolling increases to above the other two. But when you heat it up to the same temperature, the strength actually goes down much more than the other two cases. Why? Because when you have increased the amount of cold rolling, you have increased the amount of energy that you have put into this material. And that energy is sufficient to um, sufficient to decrease the strength uh, after the heat treatment. Okay. Anyway, let me stop here and put this up as um, lecture 4A, and then I will add more sets of slides and presentations after this. Okay.